Of the day. Thank you for making it on a Saturday evening, afternoon. All right. So, what I'm going to be talking about mainly today is going to be about streaming databases. Hopefully, some new learnings, but I'm not going to bore you with too many details. At the end of the session, we will hopefully have a tell and show with a couple of streaming DBs so that we actually show something rather than just talk about it. So with that, without much ado, let's begin. So I'm Pavan Keshavamurthy. I'm founder and CTO of Platform 83. We help co-organize this event, but in general, we kind of specialize in the landscape of streaming platforms, data infrastructure in general, but also Kubernetes amongst other things. My background is mostly tech, but I've also spent time doing other things. Occasional contributor. So is Avinash. Avinash, apart from managing this community, also is a full-time platform engineer. And that's his background. So please catch up with us separately if you'd like to talk. So this talk is about streaming databases. And for that matter, this community is about streaming. So whenever we talk about real time is a little... Is this better? Is this better? Previous, okay. All right, okay. So whenever we talk about real time, what even is real time, right? I mean, everything is ultimately limited by the speed of light. So what we are actually talking about is we've got hard real-time use cases and more soft real-time use cases. So if you kind of look at it as a spectrum, on the leftmost side, you've got things like HFT, where literally it's not even within the realms of attainment through software-based stream processing or any other real-time processing mechanism. That is more the world of FPGAs and such. Generally, the latency that we're talking about there is sub-microsecond, although some people will tell you that's picoseconds, nanoseconds. I mean, it doesn't matter. Those are just units at the end of the day. But you've also got other sort of the next level of hard real-time use cases around self-driving cars, industrial automation, lots of different things, which is you could think about it as a few milliseconds at an upper bound. And on the other side, you've got traditional batch processing, which is time to results offset by, depending on how functional or dysfunctional your sort of data processing team is, it could be minutes, hours, sometimes even days. So that context is kind of very important to set because when we talk about real-time processing, we're actually talking about constraints within the system. So there are constraints around how quickly you bring data from different operational systems into the realm of processing, right? And so that's really one big contributor to how fast you can get some useful insight out of data. But that's only one part, right? There is the sort of elephant in the room, which is how quickly can you do something useful with that data, which is where all the heavy lifting happens. In other words, the processing is usually the weakest link in the chain, right? And the point is, it's not, I mean, you must obviously get data in as quickly as possible in order to make streaming or real-time processing at any rate a success. We've heard some good talks today about lake houses, about how CRED is leveraging Aerospike DB in conjunction with Flink. So all of this is really about minimizing how long it takes to get useful insight out of the data. And where the data flows in is sort of, people have lots of takes, hot takes on the architecture, whether you use a lake house or a warehouse. It depends, it doesn't matter. So with that context being said, we'll talk a little bit about why stream processing is actually hard. And when we say we want to get insights out of the data in a few seconds time, what are fundamentally the constraints, both computationally as well as in other ways that makes this hard. And to put that in perspective, it's really two things, right? The so-called real insight into why stream processing is hard is that stream processing operations are actually defined on the future state of data as it arrives, or you're actually defining how data that arrives in the future needs to be processed. So unlike conventional databases or even data warehouses, or general landscape of OLAP tooling, where you're actually working on data that already exists, stream processing is actually the polar opposite. It's about defining what to do with data that has not come yet. And it's fundamentally one of those small gotchas, but the important gotchas that you need to kind of wrap your head around. And the second problem is that when data does arrive, it is not momentary. It keeps happening, right? It is unbounded, and therefore, in an unbounded world, you can't really predict what happens. Particularly in the realm of distributed systems, there is nothing that is trustworthy, not the network at any rate. So therefore, unbounded data also means that data is not necessarily going to arrive on time. Therefore, the computation that you perform on it is only so correct as the data and the time at which it arrived. So there are temporal aspects, and therefore there are correctness and consistency guarantees that you should ideally be able to offer. Nobody wants to say, like this stuff is wrong, right? You ideally want to be correct, and stream processing in particular has a sort of higher threshold on how correct it needs to be. So those got just out of the way. This stuff has been solved, right? There have been stream processing frameworks since the mid-2000s at least. So if anybody remembers, in the Apache Foundation graveyard of projects, S4 was the first. But even before that, there were a lot of sort of theoretical implementations. But like following on that, Storm was quite big, and you've had a lot of tools that have come into this landscape, continue coming into this landscape, and many are still being incubated. But the popular ones, of course, you got Spark Streaming, Flink, Kafka Streams, all of these things, right? So we already heard how CRED uses Flink. Flink is probably the most mature tooling in this space, but people who leverage Databricks, any hands that go up? Okay, so lots of Spark streaming in there. Is that true streaming or not is a question we will reserve for another day. Okay, but that brings us to, we spoke about why this is hard. Now let's talk about what will make it simpler for mere mortals like us. And my submission here is it is still a DevX problem, right? And like SQL has been around since the 70s. It's a dinosaur, but the fact is it works, and it is the best DSL ever, right? Stood the test of time, and you could do a survey, right? Like data engineers, analysts, even data scientists, whatever, statisticians, whoever you want. Everybody prefers the unreasonable effectiveness of SQL in terms of getting what you want, expressing what you want. So expressivity is still the key. So that brings us to what stream processing with SQL interface, and sort of the emergence of streaming databases, which we will talk about in a little bit. But what does this fundamentally mean? If there are data engineers here who use Flink or Spark or Storm or any of these things, what we're really talking about is, in the context of these stream processing frameworks, you've got operators. You've got filters, maps, flat maps, joins, aggregations. These are expressed typically in a functional paradigm, but being able to express that with SQL-like semantics, ideally in some standard dialect of SQL, is kind of where, my opinion, the future of stream processing is headed. And that would look typically something like this, and we'll talk through a few of these as we go. But in general, what you would want to do is you would want to look at stream processing constructs, which could be streams, tables, materialized views, indexes, and basically those being sourced or the result of such computations being sunk into typical sources and things. It could be like data lakes and like columnar storage anywhere, or it could be sources like Kafka, and being able to achieve all of this in more or less standard SQL. So some of you might already be thinking, hey, I've got Spark SQL as an interface already, or I've got Flink SQL. How are streaming databases, which is what is the discussion of topic today, how are they different? Some of you might even be thinking about, Cred also mentioned that one of the tools in the landscape is Apache Pinot. Others might have Druid. How are these fundamentally different from streaming databases? And we want to put that in perspective a little bit. So the primary distinction is that stream processing frameworks by definition, use local state stores, right? So therefore, there is an aspect of queryable state which is distributed. It is distributed across all the workers that the stream processing framework uses. And that is quite unlike streaming databases, which we'll come to in a moment. And also, as a result of that framework, the data flow, right, is sort of pretty much in the control of whoever is writing the job. Now, streaming databases, on the other hand, are in that context provide you some of the same benefits as stream processing frameworks, and in fact are backed by stream processors. But by definition, they want to hide this complexity from you, right? In that sense, they are more akin to conventional databases, where they take your query, plan it out, optimize it, and do the heavy lifting for you. And also look at storage as a first-class concern, and therefore kind of decouple you from the minutiae of like how storage is maintained locally, amongst other things. So therefore, the interface that is exposed to you is, you declare what you want, and then, the streaming database is basically responsible for figuring out how to get it done for you. And the result of all of that, most important thing, is that storage is class 1 concern. And of course, this is an inane statement, but stream processors are like, it's exactly what it sounds like. Now, real-time databases, on the other hand, mostly tend to work post-facto, that is post-ingestion, and they typically face sort of post-facto user-facing analytical queries, mostly ad hoc queries. It's not queries that are written against what should happen when data comes in, but it's more a view of kind of the snapshot of data and what you need to get out of there. Only thing is that real-time OLAP databases like Druid or Pinot, or data warehouses, real-time warehouses, the terminology differs. They are pretty fast at doing that, and kind of mainly distinguish themselves from the competition of other columnar data stores, mainly based on speed. Okay, so all that context being provided, like what are some examples of streaming databases that we want to talk about today? One of the early movers in the space was obviously KSQLDB. Who's used KSQLDB or Kafka Streams here? Okay, one hand. Okay, two. All right, Sagar. I'm not counting Sagar. Okay. So yeah, so basically KSQL is interesting. Kind of first mover in the space. Like I've got a bunch of data in Kafka. How do I have a SQL interface around it? Is literally what KSQLDB was meant to solve, over and above what you could already do with something like Kafka Streams. And Kafka Streams is kind of akin to Flink or anything else, except it is more an embeddable library rather than a full-fledged framework with resource management and so on and so forth. But we've also seen other things come up out here, and some of these databases are truly exciting because they're doing something radically different and sort of revitalizing the whole streaming landscape. It's very interesting stuff that's going on here. Examples of that, you've got Materialize, Materialize has been around since 2021. In fact, we'll go through a whole comparison. Rising Wave, also by a past Flink contributor. Delta Stream is not quite open source, so we'll not talk about it today, but it's also by the same guy who co-created KSQLDB in Confluent. So there are other things, Arroyo, there are many other honorable mentions which we will not go into, but the long story short, this is a very vibrant landscape, lots of different things coming out here, mainly with utility as the value proposition, right? That is, make stream processing easier, right? So this session is meant to be a primer on streaming databases. So we want to talk through a few characteristics of like what distinguishes one streaming DB from the other, and how you can develop a little bit of a mental model of like what fits your purpose or what doesn't, and how you'd want to think about adoption. So just with an open mind, let's talk through what are the important characteristics, and we'll go into a little bit of internals, but this session is not about the gory stuff. We want to also make way for about a 10-minute demo. Okay. So the first aspect is, whenever we talk about streaming databases, we mentioned they're going to have basically DDL statements, right? You want to create stuff, right? You want to create sources and you want to create sinks. And what sources and sinks does the streaming DB in question support? That's a main consideration. Many of them will have direct support for Postgres or Oracle CDC or CDC from various different platforms straight out of the box. So therefore, the result of that is that you can actually save one hop using something like a Debezium is no longer a requirement, because the streaming database can directly go source the write-ahead log from Postgres and bring it straight into the realm of processing operations. But that being said, there's also Kafka, right? Like most people would still have Kafka as sort of the connective tissue somewhere, right? And therefore need to keep these in mind. But Postgres was just an example. It could just be MongoDB, or it could be ScyllaDB, or anything else as well. So what sources and sinks is a very important consideration, because chances are if you are going down this path of even considering a streaming DB approach, you want to save time, right? You want to write SQL and you want to get things done quickly. The second key aspect is the SQL itself. What kind of SQL does it speak, right? And there are, of course, like a half a dozen different dialects of SQL, but very important consideration. As we will see, many of these streaming databases attempt to be more or less compliant with the PG wire protocol, so they're all Postgres compatible on the wire. The second consideration is, we want to talk, whenever we talk SQL, we want to talk about joins. The most typical use cases in stream processing are doing classic things, doing enrichment. So you definitely want to join data with something else. So what kind of joins are supported? And there is a lot of nuance here, depending on what you're using. Not all types of joins are going to be supported, and not in all models. So you also have things to consider like stream table duality, things of that sort. Also, what kind of over-the-wire formats, right? And how is schema managed? So that is an important consideration. There are lots of ways of encoding data, right? You've got Avro, JSON. Plus, besides that, on top of that, you also typically got envelope level information as to like, is that an upsert or is that an insert? What do you need to do with that data, right? What was the intent of the data? Describing that is an envelope concern, which is also in the sort of SQL layer. The third aspect is correctness, consistency. Like, there are various consistency models, but an aspect of consistency is also the full asset, at least atomicity bits. How are transactions supported? These are some of the concerns that come up. But we're also in the world of streaming, right? We spoke about what are typical myths in any distributed system. So things do arrive late, things do arrive out of order. How does your streaming DB allow you to process stuff in the face of some uncertainties is an important consideration, as also what types of windows are supported. So much of this is stuff that you would know. It would apply equally for stream processing frameworks as well. But one thing that is coming up in streaming databases today is the concept of watermarking, which is mostly, largely in the realm of stream processing frameworks, never in the context of streaming databases. But there are some very recent improvements there, which brings concepts like watermarking also into the world of streaming DBs. So think, what kind of consistency models does it support, and therefore, how can I basically deal with out of order, late arriving data, amongst other things. Fourthly, off by one. Okay, extensibility, right? Chances are, the built-in operators are not going to do it all for you. So therefore, extensibility means you should still be able to plug in your own code. Okay, so what kind of support exists for UDFs? Therefore, if support exists for UDFs, what languages, runtimes are supported? Am I going to force you to write it in a language that you don't like? Last aspect is fault tolerance. Here we are doing processing. Therefore, your streaming DB is just like any other DB. It needs to be able to recover from faults. Workers crash, things happen. Can you still hear me? Okay, yeah. So how do you recover from failures while not losing data is an important aspect. So the underpinning to that question is, how is state managed, right? We spoke about how storage is a first class concern. This relates to the same aspect. And measurably, what that means is, like in the event of a failure, let's suppose you had, a streaming query going on. What happens to your, recovery time and recovery point objectives? Are you losing data? Are you losing time? Are you losing both? How long, if yes? Finally, this is a new world. It's not quite mature yet. You would want to evaluate it based on how long things have been around. There are shiny tools, but have they stood the test of time? Are they mature? Are they usable? And can you offload it to a cloud provider, right? Rather than run it yourself. Those are all main considerations, as also who uses it. Finally, for the nerdy folks, understanding what's under the hood, how is this thing built, is a useful consideration, particularly for advanced use cases, because in this world there's a lot of benchmarking that goes on. So performance must be understood with real life benchmarks. So it is not, universally provable one way or the other. And a lot of performance related aspects finally tie into how the thing is built. So having an understanding and comprehension of what is under the hood will enable you to make better choices. All right, so with that, I want to maybe spend 5 minutes. How are we doing on time? Okay, we'll spend a little bit of time. Not going to spend too much time here. We'll skip, but for the curious people, we spoke about how conventional stream processing engines, how do they run stuff in parallel, right? So I picked a generous amount of material out of Materialize out here, but there have been different data flow paradigms. The most important consideration that you need to look at is how is data flow managed within the streaming database, particularly vis-a-vis how it would be managed in a conventional stream processing engine. So with what tends to happen is with Kafka Streams or Flink, you basically got a processor topology of different operators, and in Flink terms, all these operators basically get sharded into different physical cores, and that's kind of how parallelism actually works. So one of the complaints about the system is that there is a lot of, if you've got n number of cores, and many of these operators actually get sharded to a core, there is a lot of chatter between different cores, and that's one of the aspects of performance which particularly in terms of drawbacks when state is managed locally, you do run into bottlenecks. Now there have been I don't know if anybody's heard of in the Rust world in particular, but also otherwise mostly coming out of Microsoft research is a paradigm called timely data flow, and there have been a few sort of reference implementations based on a lot of academic papers. Particularly, there's one that comes to my mind called NIAD, and the paradigm is mainly about timely and differential data flow. So how that is different and how that ties into streaming databases is that basically all the operators in this case are kind of shared across the various compute cores, and therefore there is more cooperative data flow, much more on demand rather than unidirectional data movement, which is what DAGs do. A lot of details, but the TLDR is that if you take conventional stream processing approaches, they're typically based on directed acyclic graphs. So data moves from one operator to the other. Even if you bake in a custom operation, it gets folded up into the topology somehow. And basically your operators are kind of sharded into cores. There's a lot of cross-core data movement. New paradigms like timely differential data flow. A lot of this is theoretical CSC stuff, but there are a lot of room. There's a lot of room for optimization in terms of understanding these paradigms and what it means, mainly in the context of stream processing. And the point is, some streaming databases in particular take advantage, whereas some others stick to the the well understood path. So I'm going to take 5 minutes to just quickly walk through this. For this consideration, we looked at this whole sorry, too many animations. Okay, so we looked at a bunch of different streaming databases. For this comparison and for this show and tell, we'll in particular consider KSQLDB, Materialize, and Rising Wave. So with KSQL DB rather, the core architecture is that it is basically sort of a SQL DSL on top of Kafka streams, mostly Java, and therefore it inherits the same characteristics, advantages and disadvantages of Kafka streams underneath. So it's basically based on a processor topology. Each time you issue a SQL query, something plants the SQL query out, and then it hands it off to Kafka streams like processor topology, which actually performs the operations for you. The threading model there is similar to what we already talked about. There are two things that you need to understand. There are streams and tables. That's an important distinction to understand. Basically, you can look at tables as compacted streams, but those distinctions are very important in the context of KSQL. There are also concepts of push queries and pull queries, something that exists across all the three others as well. KSQL is not ANSI SQL compliant. Well, it is maybe ANSI SQL, but it is a custom dialect of SQL. So therefore, there is a little bit of custom out there. It supports, one of the interesting things is it integrates well with the Confluent schema registry. I know there may be users of Confluent schema registry. Anybody? Okay. Which is nice, particularly in terms of schema inference and all of that. The joins that are supported are will need to be considered in the context of whether it is a stream to stream join or a stream to table join or a table to table join. Based on that, your mileage may vary. But in general, it does support n-way joins, which is kind of interesting, but there are some pretty big limitations in terms of the types of joins that are supported. window operation supported or tumbling hopping session. There's no concept of watermarking. There is a concept of grace periods, however. So if the late arriving data does not come within a specific upper bound, then the window is considered closed. It uses RocksDB as state store. So all the advantages and disadvantages thereof. In one of the interesting things is with KSQL, you will not lose data, right? Because anything that is in the state stores is also basically backed up to a changelog topic in Kafka. However, there is no snapshotting or checkpointing. What that means is that if you've got a sufficiently large Kafka Streams job and a lot of built-up state, and you lose that node, it's on a local state store. If you lose that node, the state will need to be replayed back from the changelog. So therefore, that means your RTO is going to go for a toss, especially in some high throughput scenarios. Sources and sinks, all the 200 odd or 500 odd Kafka connectors are usable with KSQL simply as sources and sinks. You can write UDFs mostly in Java, and it is Confluent backed. It is open source, but it is community license. Okay, important consideration. It's still very well maintained, and a lot of adoption that we see, particularly of Kafka streams, but also plenty of people using KSQL DB in the wild. The second one is really about Materialize. They've been around since about 2020, and the main distinguishing factors, there are fewer concepts to learn. It is mostly based around materialized views, and therefore you've got materialized views, which are kind of aggregation of streams, but also indexes, which are kind of like tables, if you can think about it that way, classically used for enrichment scenarios and all of that. Materialize is fully wire compatible with Postgres. So whatever you write on Postgres should be in theory usable against Materialize. Interesting thing is all forms of joins are supported, including some very interesting varieties like lateral joins, Cartesian cross joins, all of these kinds of things. I'm not an expert on Materialize. We did play around. We'll show you our demo, but the whole philosophy around fault tolerance is a little unclear. So in timely and differential data flow, basically state is stored in memory in a concept called arrangements. So arrangements are mostly in memory. Are they checkpointed and all of that? I'm not 100% sure. As far as I understand, no. But there are good number of sources and sinks supported. Good number of sources supported. In terms of sinks, it's mostly Kafka. Red Panda is also pretty much compatible with Kafka. There are no UDFs, but extensive support for SQL functions. Materialize is very interesting, and they're doing great work, but it is BSL. Keep that in mind. So that is the same license as Terraform, what Terraform has gone to these days. Last one here is Rising Wave. Rising Wave comes from a former Flink contributor called Ying-Jun Wu. I think it has inspirations both from timely data flow, the Materialize paradigm, as also more conventional. Again, the concepts are mainly around indexes, materialized views, also compatible with the Postgres over the wire. All these formats are supported. In terms of joins, it looks more like KSQL, but transactions are supported. The interesting part here is that the state store in Rising Wave is custom. It's not quite RocksDB. It is something custom called Hummock, which is basically built on top of S3, I believe. So there is checkpointing and fault tolerance, basically because everything is checkpointed to durable storage. All these sources are supported. There are a number of other sort of cloud queuing stores, all of these things that are also supported. And the nice part, you can write UDFs in Python. Rising Wave is Apache 2.0, so licensing wise it is fully in the spirit of open source, and it's been also around since the last couple of years at least, but has quite a bit of activity as well. One other distinguishing factor is that it also supports, unlike most other streaming databases, it also supports watermarking, which is kind of very interesting. Why that is important is mainly in the context of correctness of your streaming queries. So I know this has been exceptionally long, but we will take some questions here now, or we'll watch a quick demo and
Right, I'll not take a lot of time. I'll just keep this very brief. So we've got a bit of a sandbox or a quick start environment for all of the three streaming databases that we discussed. So it's just a single click environment that you can play around with, execute some commands. So I'll just quickly show. We'll start with KSQL. It's a Docker Compose setup for all of the three. Maybe just quickly show the Docker Compose setup as well. There's an init container that creates all the topics that we need. By the way, this is going to be with Kafka for both sources and sinks, and we're using Confluent Cloud to keep things simple, so that you don't have to bring up Kafka cluster locally. And this works with any Kafka cluster that has the same SASL plain authentication mechanism. Just plug and play. The KSQL table server is a container that is running, which is hooked to the Confluent Cloud cluster. I've got a few environment variables that define this. It's all documented in the README if you want to play around later as well. And there's a container that has the KSQL DB CLI where you actually execute the CLI SQL comments. You could run KSQL DB as a in the headless mode where you provide a SQL file and then it executes in the background. You don't have to interactively execute the commands. So I'll just quickly show the data that is being produced to the topic. We have a console consumer that is running here, which will read the data. So there's some simple data, which is to mimic an IoT system where there's a sensor ID, temperature, and a timestamp. Very simple data. Here we'll get into the KSQL console. Clear this. Since this is already wired to the Confluent Cloud, we don't really need to set up a source or even set up a sink for that matter. We'll start off by creating We'll start off by creating a stream which will read from the topic temperature readings. That is what we're looking at the right. Maybe okay, looks like I've not cleared up the state. I already have a stream called temperature stream within my Confluent Cloud. That's why there's already an existing stream. But maybe we can just create the stream where we do a simple scalar transform. Just convert the temperature from Celsius to Fahrenheit. Right. This is also likely going to exist. Okay, this also already exists, but it's more or less the same. You run these commands to actually run this SQL query to create a stream, which is essentially consuming from the Kafka topic, and then you modify that with a select statement where you modify the data. Here, what we're doing here is converting from Celsius to Fahrenheit. We can maybe take a look at the data as well, what was modified. And this is all backed up to the Confluent or the Kafka cluster. Automatically, there's a topic that is created for each stream. If we were to look at the Confluent Cloud UI with the list of topics. Okay, I've sort of cleaned up the topics, so that's why they're not visible. Maybe I can create a stream with a different name that will we were creating the input stream, which is reading from the Kafka topic temperature readings, and the data is in JSON. And we'll also create the scalar transform. I'll just do one example for each of them. I've got a few more documented. Maybe we can try it out offline. and we're creating a stream that is transforming that data from Celsius to Fahrenheit. We could also consume it parallelly. Let's see what's the topic name. It should be the same name as the stream that we created. Okay, we've got the stream, the topic name. Sorry, we could look at it in this UI as well, but let's just do this. Okay. We'll take a look at it from the KSQLDB console as well. Yeah, we already see that the data is being streamed to the Kafka topic with the converted temperature. This is a very simple example, a very 101 example, but this is a scalar transform where we're just converting one of the values to a different value, doing some simple operations. There's also another example where we do a tumbling window for we calculate the average temperature for every 5 seconds. I'll not execute this and then look at the results, but we can do that offline as well. And the next one that we'll look at is materialize. Feel free to stop me and ask if there are any questions. I'll go ahead in the interest of time. I'll just first do a down first. Okay, we'll quickly take a look at the materialize setup, which is once again there's a init container that creates the necessary topics for us. In this case, we're creating an additional topic apart from the input topic. We're creating a topic for materialize to store the progress, so that when materialize is syncing the data back to Kafka, it leverages a topic called progress topic, where it will essentially store the offsets of how much it has synced back to Kafka. So that's one topic we're creating, and we're creating a couple more topics for the actual syncs. In the case of KSQL DB, that was already automatically created by KSQL because it's a Kafka only streaming database, so it knows to automatically create the back it up with a topic. But in case of materialize, we manually create the sync topics. Okay. I did not set a couple of environment variables for the output. Just quickly do that. Okay, going back to the Docker Compose setup, let's just quickly run through that. And yeah, the init container creates some topics for us, and we have a producer that's in Python that produces the same data, the sensor data that we just looked at. And materialize is once again a single binary, a single container that runs, and it has two interfaces. One is the web interface, which is not really a web interface. It's got a HTML HTTP server, which serves a very basic page where you can look at the memory consumption for the various streams. That's a very rudimentary interface that they have, not much of design there, but there's also another Postgres port that is exposed, that is 6875 is the Postgres port, and we can connect to this materialize DB using any Postgres client. So we've got a Postgres image running, which will use to connect to materialize using PSQL. This should be up. So we've got the command documented here in this as well. We're passing in a couple of environment variables into PSQL so that we can connect to Confluent Cloud. You could do it without it as well. Okay, next let's run some queries. So we'll start off by creating a connection to Confluent Cloud. That is, we're creating a Kafka connection, not essentially Confluent Cloud. It can be any Kafka connection. We're creating a couple of secrets for the username password that is used for Confluent Cloud, and then creating a connection for Confluent Cloud. specifying the usual suspects, the broker, the SASL mechanisms, and the username password. And we're also specifying the progress topic as material is progress, which will be used to store the progress of the syncing of materialize. And then we create a source in materialize, which is where sorry, I'll just minimize the other part. Okay. So we've created a source that reads from the topic temperature readings, the same topic that we looked at in case equal db as well. And here we have a couple of examples once again for the scalar and window transform. But first, when the data is read, it is actually read as a single, more like a string. So we format that into JSON so that materialize can we can do queries on top of it. We could do it when we create the source as well. I just have an additional step where I extract that data and then make it separate columns. And finally, we have the same query where we convert from Celsius to Fahrenheit. We could maybe look at that as well. Yeah, so once again we've done the same thing where we've converted the temperature from Celsius to Fahrenheit, and this is being streamed to Confluent Cloud as well. No, it is not yet, sorry. So in order to stream it to Confluent Cloud, we'll need to create a sync. So we're creating a sync here, which is leveraging the existing Kafka connection that we created earlier called Confluent Cloud, and we're syncing it to the topic temperature converted materialize. Let's just okay. Seem to have messed up the query somehow. We'll need a for an envelope upside. What's the other envelope? Okay, I'll fix this query, but looks like we'll need to specify the primary key as well when we're doing an upsert so that it knows when do you replace it. I seem to have made a mistake while I'm copying and pasting it. Is it? Okay, yeah. Yeah, there's no insert. Yeah, it's upsert or materialize. But the example that I did where I had primary key, I seem to have missed that when I've documented it. I'll update that in the repo. But so essentially, you create a sync for materialize to be able to send data back to Kafka once it is done processing it. We're creating a sync for the materialize view that we created earlier. So I'll not delve into that much. Just call it done for materialize and move on to rising wave. Sorry. Okay, one final demo with rising wave. Once again, it's a similar setup where with the Docker Compose we bring it up. Sorry. Okay, I'll need to change the environment variables for the output topics. Let me just quickly do that. Okay, and now bring it up. But with rising wave, we have a lot more components that are involved. Unlike case equality where materialize, we don't have a single binary. Although you could run rising wave, the core components in a single container. There are other components that you need for rising wave, primarily for the S3 store. Pavan spoke about how it uses Hammock on top of S3. So we need a S3 storage for rising wave as well. We've got the same minute producer, and then the compactor node is where it's the component of rising wave which writes the data to S3. So it's all modularized, and there's the compute node where the actual computation happens. And there's an etcd that is used for storing the metadata, and there's front-end node, which is the query interface where we'll be actually connecting to using Postgres. And there's the meta node, which deals with the metadata, communicates with the etcd, and then stores the metadata for the various processing. Mini IO is a local replacement for S3 that we're using. And finally, the Postgres client for communicating with Rising Wave. Okay, now that this is up, we'll once again connect to it with Postgres PSQL. Once we're in, we'll just quickly show how do you create a source and then a sink and a simple query. Okay, so with Rising Wave, you can directly create a table. You don't need a concept of creating a source or a connection. Although there's a concept of connection for private AWS private linking, that's a different thing. But you create a topic with the parameters for connecting to Kafka. The connector that we're using here is Kafka, and then we provide the necessary properties in topic and then the security properties. Some of these are put out as environment variables. So, and yeah, we create a simple materialize view, the same thing that we did with materialize. So it's the exact same query. We're creating a materialize view, and then we sync it to Kafka. Which one is this? Okay, that's here. So we're syncing this to Kafka. Whatever materialized view that we created, we sync it to Kafka. We can maybe take a look at it here. What's the thing called? The topic is temperature converted Rising Wave, so we can consume from it. Yeah, so we have the same data, temperature, and then they converted in Fahrenheit, and a couple of other examples as well, which I'll not run right now, but the same thing with all the three databases. Right, I'll write over. Yeah, the demo is available on this link. Feel free to check it out if you want to play around. We'll be adding more examples, a little more documentation around it as well. Right.
Okay, so sorry that was a long demo. Should have planned the time better. But in conclusion, right? So there's a lot of convergence in this area: streaming databases, stream processing, real-time OLAP, all of these things. But that's a few years away. In the short term, what's the recommendation? Consider all the three approaches. If you want stream processing, like that should be like 20%, 80-20. You could kind of split it between doing most event-driven architecture, classic materialized views, event-sourced aggregates through streaming databases. But for complex ETL, consider stream processing. Like go the conventional way, Flink, Spark streaming, Storm, whatever is your cup of tea. If you want user-facing analytics, I think you got a lot of maturity in the Apache Pinode, Druid. All of these things can still give you great performance, sub-second query latencies. So it's an interesting world. Feel free to play around with the demos. Since it's late, we'll not stop for questions, but let's connect and network informally. Thank you very much.